everyone, my name is Julie Peck, and I'm a member of the Free Flyer Technical Support Team at AI Solutions. Today I'm going to be giving you a walkthrough of one of my favorite sample mission plans, which depicts NASA's planned Lunar Gateway. So we're going to go ahead and open up the Lunar Gateway Sample Mission Plan in Free Flyer. So there are a couple of different ways to get to your sample mission plans, just to review. From the Free Flyer home screen, you can click the Browse Sample Mission Plans button, which will take you directly to the folder where all your sample mission plans are stored. This one is in the Demos folder, so we could go in here and open it up directly from this Windows Explorer. Or, since this is considered a demo mission plan, it's actually available to run right from the Free Flyer home screen in this middle section. So I'm just going to go ahead and click on Lunar Gateway. So this mission plan shows the intended orbit for NASA's Lunar Gateway. The Gateway will be a small spaceship orbiting the Moon that will act as a science laboratory, a home base for astronaut expeditions to the Moon, and a stepping stone for spacecraft bound for Mars or other deep space destinations. The Gateway will orbit the Moon in a near rectilinear halo orbit, or NRHO, a unique orbit that is possible because of gravitational forces from both Earth and the Moon. The NRHO depicted here is based on an ephemeris file that we retrieved from NASA's Navigation and Ancillary Information Facility at the Jet Propulsion Laboratory. So as you can see, we have three different views. We're going to talk about them in a lot more detail a bit later, but we'll give a quick overview here first. Here in the largest window is a rotating view. This view contains the Gateway as well as a spacecraft in a distant retrograde orbit, or DRO, this yellow one. And that's another special orbit made possible by the combination of gravitational forces from both Earth and the Moon. In the top right, we have a Moon-centered inertial view, and in the bottom right, we have an Earth-centered inertial view, and both of those also contain the Gateway orbit. As you can see in the rotating view, we're performing contact analysis between the Gateway and 4 different ground stations. One is a lunar station based at the Moon's south pole at Shackleton Crater, and the other 3 make up the Deep Space Network on Earth, with stations in Goldstone, California, Madrid, Spain, and Canberra, Australia. And these 3 are specifically designed to be evenly spaced around the Earth to give us good access to spacecraft that are working in deep space missions. So we're going to dive into a few different aspects of this sample mission plan, and we're going to go ahead and start with the contact analysis. I'm going to navigate away from the Output workspace and to the Control tab to take a look at our mission plan. So on the Control page, we can see the structure of our whole mission plan. That includes all of the objects created in the object browser on the left-hand side, as well as any blocks of freeform script or other script elements in the mission sequence section. So over in the object browser, we can see we have 4 different ground station objects, 3 that represent each ground station in the Deep Space Network. You can double click on those to open them up, as I did here. And then 1 more to represent our lunar ground station at Shackleton Crater. And this one we've just placed at the south pole of the Moon and given it a cone-shaped mask with a 30-degree elevation. We have our 2 spacecraft. The important one here for this mission plan is the Gateway. And if you take a look at that, you can see on the orbit page that doesn't look like the Gateway orbit at all, but that's because we're using an ephemeris as our propagator. And on the propagator tab, you can see that we're pointing to our Gateway ephemeris file in our definition here. We've also got 3 view windows, one for each of the views that we were discussing in our Output workspace. And then a number of vectors that we're using to illustrate when contact is occurring between different ground stations and the Gateway, as well as one that just points to the Earth from the Moon. That's Moon to Earth. These vectors are configured entirely through script, so if you double click on them, you'll see nothing happens. They're just created in the object browser here so that we can easily see them and reference them from our view windows. So we can open up all of our freeform blocks by using the Open All Freeforms button or just by double clicking on each one. I'm going to show here how we set up our contact vectors. So you probably remember from the mission plan, you can take a look again at the output, that when Gateway is in contact with the ground station is green, and there's a green line drawn between the two. So that green line is represented by the vectors. And here's how we create them. Very simple to do. We use the vector name. For this one, it's Canberra to Gateway, and then the build vector method to say we're going to build this vector from the Gateway to the Canberra ground station. So to give an illustration of this build vector method, I'm just going to type this out again. So I'm going to comment out the existing code and just retype the thing. So this should also give you a good introduction if you're not familiar already with FreeFlyer's autocomplete capabilities, which are very handy. So I can go ahead and choose Canberra to Gateway and hit enter to select. And if I type a period, I'll get a pop-up list of all of the available properties and methods on this vector object. We're going to use the build vector method. And when I type an open parentheses, we see there's a lot of different options for what type of vector we want to build. So this is a really handy interface that just shows you a bunch of different ways to create custom vectors within FreeFlyer. There's also a lot of different overloads to this method, which you can scroll through and see all the different options using the arrow keys, but you don't have to. It's just for your benefit at this point. So our first argument to this method is going to be the number 9, because this is an object-to-object vector. We want it to go from the Gateway to the Canberra ground station. Our second argument is going to be Gateway. That's our spacecraft. And then our third one is going to be Canberra. And again, you're seeing me take advantage of that autocomplete capability in FreeFlyer scripting. So now that we've got the vectors built, we can set all of their colors to lime, because lime is a nice bright green color that indicates happy contact. And then we're going to start them all turned off. So you can turn your vectors on and off in the view using the active property. And if you hover over that, you'll see this description pops up saying, okay, this is indicating whether or not to evaluate the methods of the vector and draw it in the mission view. So we're going to turn them all off to start. And then in our propagation freeform, we can implement logic to say that if the Gateway is in contact with the ground station, we can set that particular vector to active, and then it'll be drawn in the mission view. This also controls the color of the ground stations, so we can see, okay, if contact is achieved, then Canberra is going to be green, or lime rather, and if it's not achieved, then it's going to be red. And that's how we see it depicted in this mission view. Any of the DSN that are not in contact are red, and the ones that are green. We can also use our replay toolbar up at the top right to kind of try and go back to a point where the Shackleton Crater ground station is not in contact as well, and then it's a little bit easier to zoom in. So we can see that when we're not in contact, we're being blocked by the moon, in this case. The Shackleton Crater ground station is red, and there's no vector being drawn from the Gateway to it. But we can still communicate with the Earth, which is nice. So that's another really excellent feature of this NRHO, is that we can spend a lot of time in contact with that lunar ground station, because during most of our orbit, when we're moving slowly at apoapsis, we're looking directly at it. It's on the south pole of the moon. At the same time, the orientation of the orbit allows us to maintain almost constant contact with the DSN here on Earth. I'm going to move on here to talk about some of the different viewpoints in this mission plan. So we're actually going to start with the Earth-centered inertial view down in the bottom right. This is a view that's probably pretty familiar. We see the Earth at the center, and the moon is moving in a roughly circular orbit around it, as shown by the white line. When we put the Gateway in there as well, we see that from the Earth's point of view, the Gateway will move along with the moon, and we'll see it move to the south, further away from the moon, as it reaches lunar apoapsis, and then closer to the moon as it reaches its periapsis. It creates a nice kind of spirograph style image when it's viewed in this frame. Up above this window, we have the moon-centered inertial view, and this depicts what the Gateway's orbit would look like if you stood still at the center of the moon. So this is kind of interesting because it looks totally different from any other views that we've seen. And you might notice that the orbit almost looks like it's kind of divided into quadrants. We sort of have 4 different chunks of orbit tail here. Well, this is interesting because the Gateway's orbit period is about 7 days, and 7 times 4 is 28, which happens to be the period of the Moon's orbit around the Earth. So if we switch over here in the Output Properties tab, you can easily switch to a body fixed view of the Moon. And when we look at it this way, we can see that the sort of rotation rate, for lack of a better term, of the orbit itself actually lines up with the rotation rate of the Moon. Now, as we know, because we can only see one side of the Moon itself is tidally locked with the Earth. So we can almost think of the orbit also being locked with the Earth as well, and therefore we never get into a situation where the Moon is blocking communication between the Deep Space Network on Earth and the Gateway. And that's exactly what we saw in our rotating view when we were doing our contact analysis. So this brings me to the main window here, which rotates with the Earth-Moon system. And just as a handy tip, you can right-click in any window and click Reconnect Automation to bring you back to the default scripted view. Just to recap exactly what's going on here, we've got 4 ground stations. We also have the L1 and L2 Lagrange points for the Earth-Moon system, and the Gateway in its NRHO, as well as a sample distant retrograde orbit, or DRO. So the NRHO and DRO are both special orbits that exist in any system that can be approximated as a circular restricted 3-body problem. That is, any system where 2 bodies of significant mass, in this case the Earth and the Moon, move in circular orbits around the very center of the system, and the 3rd body, in this case our spacecraft, has negligible mass by comparison. This type of problem is represented by the Sun-Earth system, the Earth-Moon system, and numerous other planet-Moon combinations. Distant retrograde orbits, like this yellow one that we see here, are stable solutions to the circular restricted 3-body problem. That's to say, they're not highly affected by perturbing forces and therefore do not require frequent station-keeping maneuvers to maintain the desired orbit. Now the NRHO, on the other hand, that's intended for the Gateway, is unstable and does require station-keeping maneuvers to avoid drifting out of the orbit. However, the cost of those maneuvers is by and large outweighed by the fantastic communication access that we get between the Earth and a potential lunar ground station from the shape of this orbit, and also the access that we get to the lunar surface at periapsis or deep space at apoapsis here, where you can launch into larger missions without having to expend a lot of energy to get out of the Moon's gravitational well. So setting up a viewpoint like this that rotates with the system really helps us to understand the shape of the NRHO, and I want to talk about a couple of different ways that you can do this in FreeFlyer. This sample mission plan uses a simple 3D view, but it sets the reference object to be a coordinate system that's centered on the Moon and defined by the L2 libration point, which we configure in FreeFlyer script. So I'm going to jump back over to the control screen here to talk a little bit about that. In our object browser, we've defined 2 rotating libration point objects, EarthMoon L1 and EarthMoon L2, and as you might guess, those represent the L1 and L2 Lagrange points for the Earth and Moon system. So in our second freeform, under Setup Objects, we configure these libration points. In FreeFlyer, if you right-click on any object and then select Go to Help File, you can learn some more information about the object type. And so here we see the rotating libration point object allows the user to set up a rotating libration point coordinate system, and it also allows you to retrieve handy information like the distance from the libration points to one of the 2 centers or the very center of the system. You can also learn more about rotating libration points in FreeFlyer on the guide page, and so I just clicked on the link here, but this guide is under Guides, Interplanetary Analysis, and Rotating Libration Points in the help file. And this gives you a nice overview of how these work in FreeFlyer, so I definitely recommend taking a look at that if you're interested. So after we've named these objects in the object browser, again, this is an object that's configured in script, so if we double click on it, nothing happens. Instead, we set it up here using all of these different properties and methods to define our system. So we say, okay, our primary system for this Lagrange point is the Earth. The secondary system is going to be the Moon. We define which libration point we're talking about by saying L1 or L2. We set the reference body in this case to be the Moon, so that's going to be the distance that would be computed. And we turn recompute barycenter to 1, which just means that all of the bodies in the system will be used to compute the system barycenter, rather than just treating it as the primary, which would be the Earth. Once we've set up our libration point, we can use them to define a custom coordinate system, which we do in the define RLPCS procedure. So in this mission plan, that's under the setup output freeform up here at the top. This procedure retrieves the direct cosine matrix from the rotating libration point, which represents the rotation from MJ2000 to the rotating frame. And then it uses that rotation to define the axes of a coordinate system. So here we've created vectors x and y and a position vector. And we use the getDCM at epoch method to retrieve our direct cosine matrix and then assign the elements of that matrix to the x, y, and z vectors accordingly. We then use the x and y vectors to build our coordinate system. So this is the build coordinate system method, which is very similar to the build vector method that we were talking about earlier. This position specifies the position vector to the origin of the coordinate system, which in this case is going to be equal to the Moon's position with respect to the Earth, and this way our view will be centered on the Moon. In our view window, RLP view, we've already set up our viewpoint to be a 3D view that uses the rotating libration point coordinate system as its source and target. So we're all good to go. And all we need to do is call this procedure to configure our coordinate system at every propagation step, and the view will update accordingly. So in our propagate freeform, down towards the bottom, right before our update commands, we call that define RLPCS procedure. And again, that creates this nice view that rotates with the Earth-Moon system and gives us a really good idea of what the NRHO orbit looks like and why it's so useful. I wanted to go quickly over another option for configuring a similar view. So in this instance, we explicitly configured the rotating libration point and custom coordinate system objects just for clarity and to demonstrate how these objects can be used when analyzing systems like this. But another option is to simply use a rotating pulsating viewpoint in your view window. So if we go back to our RLP view on the viewpoints tab, our current selection is 3D view, but we actually support a built-in rotating pulsating view type. So if we switch that to rotating pulsating view, we can see it auto-populates with the primary object as the Earth, the secondary object as the Moon. And then I'm going to set the center mode, instead of offset, I'm going to set that to object so that we can center our view on the Moon. And this use pulsating mode checkbox just means that the view will pulsate as well as rotate, and that means that it'll automatically keep the distance between the Earth and Moon in the view at a constant. So I'll hit OK. And if we run our mission plan with the new configuration, we'll see that our view isn't set up quite as nicely as the other one because that was the default for this sample mission plan, but we can just rotate this around to get to a similar setup. And as you can see, it produces very similar results to the original, where we explicitly define the rotating frame, but it's actually even simpler to set up. And I'm just going to stop this because we don't need to watch it run all the way to the end this time. So I'd like to finish off with just a quick visualization tip. You probably noticed that our Gateway's spacecraft tail changes color as it moves around the orbit, and I think this is just one of the really fun features of FreeFlyer. You can set this up using the interpolate color RGB function. And in this mission plan, that's in freeform 4, right at the top of our propagation loop, we say gateway.color equals colortools.interpolate color RGB. And then you pass in an array of colors and a weight. So in this case, we're interpolating between blue and orange, red, and maroon, and the weight is determined according to the velocity magnitude at the current point. So that means that when the tail is moving fastest near periapsis, it's going to be maroon, and it's going to be blue when it's moving slowest near apoapsis. You can learn some more cool tips and tricks for visualizations by visiting the Free Flyer blog on our website at ai-solutions.com. That's all I have for today on our Lunar Gateway demo. If you have any questions, you can always reach out to our tech support team by emailing techsupport@ai-solutions.com or give us a call at 301-306-1756, extension 2. Thanks!